So the other main type of way that we detect organic compounds is with what's called high performance or high pressure liquid chromatography. It could be either way. Depends on, I think more high performance is nowadays. It used to be high pressure because we were putting it under pressure, but now it's really high performance. But the main part of it is LC, or liquid chromatography. So GC, you have to make everything go into a gas so that it can go and flow through that column. And so a compound that doesn't become a gas, or it's really hard, it's got a very high boiling point. Even though if it's less than 300, it's still, you're going to maybe break down the compound if it gets too hot, or, it's just so big that it doesn't go through at 300 and becomes a gas real easily. It's just really sticky and stuff. What we do is we use an LC, so that's liquid chromatography for it to go into a liquid. So common compounds that this works with are things like 2,4,5-T, so that is, I got it right here, trichlorophenylacetic acetic acid. We've got different fluoro groups. We've got different compounds all stuck together. They're big, they're complicated, and everything. And so usually these compounds, pharmaceuticals, we'll talk about those later on, are PFAS. I'll all be used doing this, so we'll talk about PFAS. We'll talk about these different compounds. They're all going to be using this. HPLC has a similar type of concept, is that you're separating compounds and then you're detecting them. So what they have here is you have your sample is being injected and it goes onto a solid phase column. Okay, so you put it onto that solid phase. Okay, so you inject it in as a liquid, and water is not as big of a deal here. And you inject it into it, and then the organic compounds are really absorbed onto that solid phase. Okay, then what you do is you have a pump, and you have what are called the mobile phases. So I'm going to start pumping one compound through this column. Okay, and as that compound is coming through, certain compounds will come off. And then what we do is we usually have two different phases, and we're usually going from one to the other, and we're switching them, and so the ratio is different on the two compounds, and we slowly inject one and we decrease the other. And as we do that, different compounds will be coming off of there. Common ways this happens is like with pH. So certain compounds will come off when we change the pH, so we'll be starting and we'll be injecting things into there to change the pH, and as you hit a particular pH, the compound will come desorb from the column. Once they become desorbed, they go into a detector, a mass spec we just already talked about, then usually a mass spec. You can also use a UV light, because a lot of organic compounds will have a UV light that will excite them. We're looking at flow cytometry for microplastics right now, and some plastics and stuff like that, organics will have a natural fluorescence. When you expose it to different wavelengths of UV light, they'll fluoresce. And so you don't even have to put a detector in there, you're just using a fluorescent light into there. And so that's your basic of your LC. So you have partitioning here based upon the mobile phase versus the stationary phase, and the movement between these two. So separation is based on an analyte's relative solubility between two liquid phases. So you've got the liquid phase that's on the stationary phase, and it's moving to the solvent phase, which is the mobile phase. And it's being absorbed and desorbed onto here, and the solubility of this, and then it'll finally come off of the column in there. So HPL separation, different analytes have different equilibrium between the mobile and the stationary phase. So again, this is where analytical chemists are wonderful. They actually understand all these variations. They come up with the methodologies. They standardize them for us. We're applied chemists, so I don't come up with these things, but they all do. Equilibrium is dynamic, so it's changing as the compounds are coming there. Thus, we can view it as a given analytical molecule spending a fraction of time dissolved inside the mobile phase. So it's very dynamic. So how fast? So if it's just slightly soluble, it'll only come off a little bit, but then all of a sudden you increase what that compound it likes to be in. All of a sudden it's going to go like, oh yeah, I'm going to be in the mobile phase now. So we're looking at increasing what maybe it's slightly soluble in, and then as you add more, it gets happier and happier. Since different solutes give different fractions, a separation of analytes occurs as they are pushed through a column by a mobile phase. So you usually have these very short columns. The column we had on the LC we had upstairs was only about 2-3 inches. You can get them up to 8 inches. Again, you put the solid phase depending on the compound you're looking for. So all methodologies will have, like, what should the solid phase be? There's certain ones that are for C10, C this, you know, and you can different mobile phases or different solid phases. And then you use different compounds that you're putting into it to get it to come off. And so you actually have to, so one of the problems I have with a lot of these shows, that criminal shows, where they give them the thing and then like 2 minutes later they're like, yes, and this paint was only from these particular manufacturers because it's got this distinctive, and they show a chromatogram and everything like that. As you're probably hearing, you have to know a lot about the compound you're looking for in order to know if you've got the compound into it. So like these things, you have to know something about, oh, I'm going to look for TCE, I'm going to look for 2,4,5-D, I'm going to look for DDT. You have to have an idea of what you're looking for, or class of compounds, in order for them to react the same inside of here. You can't just put in anything and find out, because I've had that happen when people hand me a thing of water and say, what's in it? And they're like, wow, what do you want me to know? To test for? You want me to test for these things? Well, yeah, test for that, and this, and this. And then you're like, well, okay, each one of those tests is totally different from each other, and they take different amount of time. And so it's not the super fast. Now, like First Environmental, you pick what compound you're looking for in your sample, and you check it, and then it'll do all the different ones. So you could test for everything in, under the sun. But the problem is every time you add a new test, you add another one of these things, you might increase your cost, because you actually have to understand the organic compounds you're looking for in order to detect them. Now, there are some new things coming out of the chemistry department that I'm learning about that I'm like, ooh, yeah. Like some of their new GC, they've got a quadrupole over there that really, the amount of compounds that it can detect is just really large. So the library that comes off of this one standard thing is really big. And so that's how you can do it, is as analytical chemists have said, well, I can't just detect VTEX compounds. I need to be able to detect all these things. They've worked on methodologies in order to improve it and increase it. And so, I'll move me out of the way here. So like dissolves like, so there's different modes. In normal phase, right here. Hi, I'm in the slide now. In normal phase, the analyte will be partitioned preferentially into the mobile phase, providing little interaction with the stationary phase. This is not desirable since selective retention on the column will be very hard to control. It can be controlled by modifying the stationary phase, a very time-consuming, expensive proposition if it's even feasible. So in reverse phase, the opposite is true. The analyte will be partitioned preferentially to the stationary phase, and by simply modifying the mobile phase by adjusting the polarity, ionic strength, the pH, the selectivity, can cause the control. So these are the different ways that each PLC works. They either work in normal phase or they work in reverse phase. So, yeah, there you go. So normal phase is the polar stationary phase and a nonpolar solvent, and reverse phase is nonpolar stationary phase and a polar solvent. So that's how we separate compounds. Again, the detectors we use can be different. So we can use UV light. So there's a whole bunch of different wavelengths that we use here to look for different types of compounds. Certain things will come off at certain UV measurements in here. You can see the different ones that are on here. Again, we are applied chemists. We're not analytical chemists. So what we do is we go, this is the standard method. This is what everybody uses. We're going to follow what everybody else uses. Our big contribution to this is looking at it in the environment. How do we detect it in dirty samples? How do we, what does it mean for environmental consideration? We are not chromatogram. We don't study that, no. You can use different wavelengths of light. You can use multiple wavelengths. So what will happen is it'll switch really fast between these different wavelengths. You can use fluorescence, you can use mass spec again, you can use electrochemical, so there's a lot of different ways. And again, you get the chromatogram over here, and so you have time retention, you get peaks inside of here, and then each one of these peaks, there's a detection of what time these compounds come off. So if you've got a particular column that's on there, so here's a C18 column versus this one's good for carbon and nitrogen compounds. So this one's really good for 2,6-dinitrotoluene. So this one's column is really great for all these different types of compounds with nitrogen into it. This one's really good for things that are really large, like in the C18 size, plus or minus a couple carbons. And so, like if you looked at some of these, 4-nitrotoluene, in there, it'll separate them out. Now, you can notice that some of these peaks are kind of on top of each other, and it's really hard to separate these out. Here, they've done a little enlargement in there. But say you're really interested in compounds 2, 3, and 4. So in this mix that's in here. Well, this might not be the best one for what you're doing. You really might be, this one's great for number 12, number 13. Another column might be really good for different types of columns. So, in Perfect, you try different columns out, you look at it, or as you read papers, you kind of see what methodologies they're using. Okay?